So, good morning and happy Monday to everyone. Today, again, we're going to continue with something completely different from what we have seen so far in terms of methodology. And in some sense, again, allow me to reiterate that we're just scratching the surface of how rich and diverse the theory of differential equations can be. So we're going to look at the heat equation, which is an example of a partial differential equation. And we're going to look at the method of separation of variables. And the other very important thing that we're going to do is the study of eigenvalues and eigenfunctions. Okay, so first of all, let's start with the fact that in the theory of differential equations, we studied the relation between the rate of change of an unknown function and the function itself. And by doing so, we're trying to find the corresponding function. Sometimes we have an initial value problem, but what is interesting about the whole process is that when it comes down to applications, in most cases, you do not have just one variable. And take a look at the simplest case, meaning the case where you're studying something that takes place in space, in the space that we live, which happens to be three-dimensional. So right away, you will see that the number of variables that we need in order to describe things that go on here is much larger than one variable. So that means that potentially, I mean, you know, if you have to look at the motion of a certain object, you might as well have to use four variables. Three variables that describe space and one variable that describes time. So no matter how you cut it, in most cases, you will need to actually work with more than one variables. When you have functions that depend upon more than one variables, then you don't talk about an exclusive rate of change, but you're talking about a rate of change with respect to a particular variable. That's the notion of partial derivative. So a partial differential equation is an equation that will involve an unknown function along with its partial derivatives. And the partial differential equation that we're going to study today, the one that describes heat, is as follows. So we have an unknown function u, and the partial derivative of u with respect to t should be equal to a number beta that, as we're going to see, is going to be we're going to say that it's a positive number, times the second partial derivative with respect to x. So in this case, we're going to be studying the mathematical model. Again, we said before that when we give a description of a particular instance that a differential equation occurs, we don't mean that in any way that that description is specific to that case and only that case. It usually means that if you find some other situation that can be modeled using very similar mathematical parameters, then you can apply that very same method to that case. So here, what we're thinking of is a rod, and we know how the heat is distributed for the beginning of time. And we would like to know how it propagates, how it changes on the rod through time. And the temperature, the heat, if you will, is given by the function u of x comma t. So we have one dimension for space and one dimension for time. And this is the differential equation. And one thing that I want to make plain right from the get-go is that in the case of partial differential equations, the domain over which they're defined is of the utmost importance. And let me try to elaborate a little on this. So remember that up to this point, we studied either general differential equations or initial value problems, right? And in most cases, we took an initial value problem to be something of a nuisance. So we had our differential equation, and then we said, oh, you know what, if you have an initial value problem, then don't forget to plug in the data from the initial value problem to the general solution in order to find the solution of the differential equation, right? And in some cases, don't tell me that you didn't think about it when you were solving something like that. You told yourselves, why did it have to be an initial value problem? Why wasn't it just a general differential equation so that we solve it, we finish it, and that's the end of the story, right? Don't tell me you didn't have a thought of that type. Everything changes the moment that we cross over to partial differential equations in the following sense. The domain of definition over which the differential equation is defined, and so the initial conditions, sometimes we're going to call them also boundary conditions that need to be satisfied by that equation, are of the essence in how we're going to actually work with that equation, how we're going to solve that problem. Okay, so in some sense, you will see that once I give you this differential equation, I have to be very specific about where the variables are defined. And by the way that they're defined, I'm going to decide how we're going to decide how to actually solve this problem. So here, in particular, we're going to say that x is between 0 and L. Think of L as the length of the rod, and that t is greater than 0. Of course, you can easily replace this with greater than or equal to. And so this is the differential equation. Once now I give you the domain of definition, I need to accompany the differential equation with a boundary or initial value problem. Sometimes you call it both. So here, I'm going to look at the insulated case. So I'm going to suppose that the temperature at the ends of the rod is constant, remains constant throughout our observation, and it's equal to 0. Okay. And secondly, that the distribution of heat is known for time t equals 0. And so this is the typical problem that is given to you. And so in other words, you have an equation, you have a domain of definition for that equation, and you also have a couple or more. I mean, the number of these conditions is going to vary according to the boundary. If you wish to visualize this in the space of the variables, then here's how it goes. And I think this is a very useful visualization. So imagine that this is the x-axis and this is the t-axis. Okay, so you're interesting for x between 0 and L, and then t can be greater than or equal to 0, which means that this is the domain where this problem is defined in the xt space, right? And if you see what this condition tell us, they tell us that we know the initial distribution. That's the second condition. We know that the initial distribution of temperature, and the first condition really tells you that along these vertical lines of the domain of definition of this differential equation, the temperature is also known. So the function is also known, and it's equal to 0. Okay, that's how this works. Any questions, please? Questions? Okay, so now the question that comes up is, how do we solve this problem? And I would like to outline the method. Okay, so this is going to be much different from anything we have seen so far. But as you're going to see, that there's one thing that is of interest here, and that thing is that we're going to have a very special way of solving this problem that does not take us through the theory of functions of several variables. So mostly, we're going to work with functions of one variable. That's the interesting thing. Okay, that's what is interesting about this problem. So we're going to first start wondering what kind of functions could possibly be solutions of this problem that have a very, very special form. So we will want those functions to actually be functions of several be functions that can be written as products of quantities in the two variables, x and t. That is by no means a general description that such functions should have. But this is what we're going to require. Okay, so we're going to require that they look like this. Okay, so I'm going to look for functions that look like x of x times t of t. Now, these functions that we're going to find, we're going to determine them, are going to form too narrow of a class to actually satisfy any general problem that we have. And as we're going to see, we will want to actually take a combination of such functions in order to get a solution that will satisfy the conditions that we have here. So, in other words, as we're going to see, our focus while finding these special functions that we're going to call eigenfunctions, our focus is going to be just this condition. And eventually, we're going to actually use the last condition at the very end in order to find specifically the functions that we satisfy the problem. In doing so, we're going to come up with a very interesting realization that we would like to be able to expand a function in terms of sines and cosines. This is going to lead us to a very, very interesting theory, the theory of Fourier analysis, which is one of the things that we're going to encounter here. Okay? Does anybody have any questions, please? So let me start by asking myself, can I find functions that satisfy the differential equation and the first condition that look like this? Okay, so can anybody tell me any functions whatsoever that you can think of that satisfy the first two conditions? There is something very obvious. That's why I'm asking you if you can think of any functions that could possibly satisfy such a condition. The answer that I'm looking for is the function 0. And basically, what is going to happen here is that we don't wish to work with a function 0. That's what the story is here. So for this reason, we will want to find non-zero functions. So we're going to take this expression and we're going to plug it into our differential equation. And what will that give us? The derivative with respect to t is going to simply be x of x times t prime of t. That's how we take derivatives of such functions. And the derivative with respect to x twice, remember that when you take partial derivatives, whatever expression you have with respect to the other variable is considered to be a constant. Okay, and this one is going to be x double prime of x times t of t, right? Okay, so If we plug them into our equation, then that's going to give us x of x times t prime of t is equal to x double prime of x times t of t. And what we're going to do now is pretty much separate the two variables. So we're going to get x of x, or t prime of t, if you like, over t of t is equal to x double prime of x over x of x. While we do this, somebody might say, wait a moment. How can you do that if you don't know that the quantities by which you're dividing are equal to are not equal to zero? And the answer is that when you do manipulations of this type, you always at least accept that you're not dividing by functions that are equal to zero everywhere. They may be equal to zero at some points, but that doesn't mean that you cannot divide by them if they're different from zero at when they're different from zero at certain other points, right? So there's an interesting remark here, and this remark is going to be pretty much the basis of what we're doing. You have an expression of t on the left, so this is an expression of t. And an expression of x on the right. Okay. So the only way that these two expressions, one depending only on x, the other depending only on t, can be equal to each other is if they're constant, if there are really no dependence. And that is going to be our starting point. So this is exactly how we will be able to start with a partial differential equation and then make it look like or eventually handle it by using relations of I'm sorry, the theory of ordinary differential equations. So I'm going to now call this common number lambda. So I'm going to say they have to be both constant. They have to be both constant. Because if they were not constant, you could just change the x and the t on the two sides, and they would never be equal to each other. That's pretty much the idea here. So they have to be constant. Okay. And remember that our goal is to find expressions that are non-zero, right? So my starting point will be to take this equation and see what it translates to. And basically what I see that I get is that it's x double prime over x being equal to lambda, which can be written as x double prime is equal to lambda x, or x double prime minus lambda x is equal to 0, right? On the other hand, remember that I had the condition. So remember that u, and this is where you see how important it is to actually take the conditions that were given with the differential equation. So I have u of 0 comma t equal to u of L comma t equal to 0. What does this translate to? It translates to x of 0 times t of t is equal to x of L times t of t, and this has to be equal to 0, right? Now, ask yourselves, what will happen if for a single value of, if x of 0 or x of L were different from 0? So if x of 0 was different from 0, then t of t would have to be equal to 0 for every t. Please see that I used the 3 lines here. I know that some of you may not be acquainted with this symbolism in mathematics, but it really means that they're identically equal. So if x of 0 is different from 0, then t of t would have to be equal to 0. But if t of t is equal to 0 for everything, then that really defeats what we had seen, or our initial requirement that we find a non-zero function. Okay, so what this means is that hence x of 0 has to be equal to x of L, and this has to be equal to 0. So now we take things together and we get what is known as an eigenvalue problem. And this is what I would like to discuss extensively. So we really forget about the initial differential equation that we had, right? Take just this with the condition that x of 0 is equal to x of L is equal to 0. So this is an eigenvalue problem. And what do I mean by this? Eigenvalue means special value. Okay, so it's, since it's a German term, it's important to understand what it means in English. So this means special value. And the thing that is special about these values is that we expect for those values to get non-zero conditions. I'm sorry, non-zero functions. So this is an eigenvalue problem. So we wish to determine lambdas such that we can find a non-zero solution. So what I mean by this is that if you look at this equation carefully, you will realize that it's not a just one differential equation. For each lambda, you have a different differential equation. So we want to determine the differential equations for which we can find a non-zero function that satisfies the differential equation and also satisfies these two conditions. And I want you to understand that these two conditions are not the same as initial value, as the conditions that you find in initial value problems. I want you to understand this, that they're not the same. Okay? So let's pause here and see if you have any questions so far. Do you have any questions, please? That's a great question. If we're going to do this with numbers? The only thing that is going to be more precise, if you will, or more well identified if you look at the initial problem, is that I'm going to tell you what beta is and what L is. Okay, so in what we're doing right now, obviously you don't know what L is, right? If you look at this problem, that's the only thing that will not change. The lambda will still be there. The lambda will still be there like this. Okay. Any more questions? Okay. So so how do we proceed? Well, we know how to solve this equation. It's an equation of the second degree. What is the auxiliary equation? So the auxiliary equation will be r squared minus lambda r, lambda, not r, is equal to 0. Okay, and can anybody tell me what are the roots of this equation? What are the roots of this equation? Great. Okay, I agree with you, but here's a small problem. Because otherwise you would think, why am I asking such a silly question here? Don't I know how to take the square root? The problem is that the roots of this equation have to do with whether lambda is positive or negative, right? So here's where I would like us to consider the different cases. So let's first of all start with the case that lambda is greater than 0. Okay, so what happens if lambda is greater than 0? Then it's exactly the roots that you told me. So r is equal to plus or minus square root of lambda, right? And in that case, the general solution of this equation is going to be x of t is equal to c1 e to the square root of lambda times t plus c2 e to the negative square root of lambda times t. Okay, so that will be the solution in this particular case. Okay, so again, the question that we need to ask ourselves here is, can we choose C1, C2 so that the solution is non-zero? And what's the problem? The problem is, and don't forget that we need to be able to satisfy this condition right here. It's easy for anyone to find the solution. Okay, that's not the big deal. The big deal is, can you find that solution that satisfies this extra condition that was given, and so that C1 and C2, or at least one of the two, is non-zero? Can you do all these things at once? That's the hard part. Okay, that's the hard part. And pretty much here, as you're going to see, the answer is no. And let's see why. Plugging t equals 0, what do you get? If t equals 0, then you get C1 plus C2 has to be equal to 0. And if t is equal to L, you will get C1 e to the square root of lambda times L, the L is outside the square root, plus C2 e to the square root of lambda times L with negative, I'm sorry, here, is equal to 0. Okay? And now you will realize that the first equation implies that C1 is equal to negative C2. And if you plug this into the second equation, then that will give you minus C2 times e to the square root of lambda times L plus C2 e to the negative square root of lambda times L equals 0, which means that you get C2 times negative e to the square root of lambda times L plus e to the negative square root of lambda times L is equal to 0. Yes, but this quantity here is different from 0. Can anybody explain to us why this quantity has to be different from 0? Can anybody tell us why this quantity has to be different from 0? You have to remember how the exponential function works. The exponential function is increasing, and this number is less than that number, right? So there's no way. So e to the negative square root of lambda times L is different from e to the square root of lambda times L. So their difference, which is what you essentially have there, cannot be equal to 0. Okay, that's what is going on here. That's what is going on here. And so since this is different from 0, that implies that C2 has to be equal to 0. Yes, but if C2 is equal to 0, then unfortunately C1 is equal to 0. And that is trouble. That's exactly what we didn't want to have. Okay. So, so what do we do? What do we do? We say, okay, fine, there's no positive eigenvalue. So let's look at 0 now. So what happens if lambda is 0? If lambda is 0, then the auxiliary equation, again, let me remind you what the problem is. Why don't I write it here so that you all have it inside? X double prime minus lambda x is equal to 0, and x of 0 is equal to x of L is equal to 0. That was the problem, right? So if lambda is equal to 0, then you're looking really at the differential equation x double prime is equal to 0, which has r squared is equal to 0 is the auxiliary equation, and r is equal to 0, double root. So what is the solution in this case? It's C1t plus C2, right? Or C1 plus C2t if I want to write it the way I had presented the solution. It's exactly the same thing. Okay, so now we're asking the same question. Can we find C1 and C2 that are less than, that are different from 0, at least one different from 0, that will give you a non-zero solution? Well, again, let's plug them into the into our conditions, these conditions right here. Oops, I erased them. These conditions right here. So you will have x of 0 is equal to 0 translates to what? To C1 is equal to 0. And x of L equals 0 translates to what? C1 plus C2 L is equal to 0. But do you see how these conditions now imply that both C1 and C2 is equal to 0? Okay, so that's trouble again. That's trouble. So this doesn't work. This simply doesn't work here. So what is our last hope? What is our last hope? Lambda less than 0. Lambda less than 0. What happens if lambda is less than 0? Again, this is the problem that we're looking at. Okay. If lambda is less than 0, then the auxiliary equation is r squared minus lambda is equal to 0. But do you see what happens now? Do you see that if lambda is less than 0, then this is greater than 0, right? So you have r squared plus a positive number equal to 0. This is where you have complex roots, or more precisely, imaginary roots. So the roots here will be square root of negative lambda times I. The I is outside, and you have plus or minus. So this tells you that the general solution, yes. So exactly because, so the question was, do you need to separate this in all those cases? And the answer is yes, absolutely, for the following simple reason. Because the solution of the system is exactly the solution of the differential equation is exactly different with respect, depending on what the auxiliary equation is. Yeah, I mean, the nature of the solution changes so much. So you indeed need to have that. So what do you get? You get x of t is equal to c1 times cosine of square root of negative lambda times t plus c2 sine of square root of lambda times t. Okay, and again, the question is the same. Can we find C1 and C2 so that this whole thing is different from 0? Please remember that we were not able to do it in the previous two cases. In the previous two cases, we got stuck and we realized that it doesn't work. Okay, so this is our last hope. This is our last hope. If this doesn't work out, if we don't find non-zero solutions, then the whole method that we chose from the very beginning really doesn't work. Okay, but let's see what happens. So what does x of 0 equals 0 translate to? If you plug in t equals 0, then sine of 0 is 0. So what you get is c1 is equal to 0. That's what you get. Right? So c1 has to be equal to 0. That's not a great sign. We were expecting to get. So we just learned that c1 has to be equal to 0 for the condition to be satisfied. I remember, I repeat, because cosine of 0 is 1 and sine of 0 is 0. So when you plug in t equals 0, this quantity becomes 1 and this quantity becomes 0. And so that gives you c1 is equal to 0. Is everybody with me? So what do we want? What do we want? We want to check the next condition. Let's see if there is any hope there. X of L is equal to 0. So first of all, discount C1. C1 is 0. Don't even bother with it. This translates to sine, to C2 times sine of square root of negative lambda times L equal to 0. Okay. And this is where our last hope lies, because if we wish to have C2 different from 0, then sine of square root of negative lambda times L has to be equal to 0. And finally, we bring things under control. Why? Because we do know what are the numbers that have sine equal to 0. What are the numbers that have sine equal to 0? Specifically positive numbers. Again, to some of you that may be a little confused here, seeing that square root with that negative lambda, and may be thinking to themselves, oh my God, are we taking square roots of negative numbers? No, we don't. Remember, lambda was less than 0, which means that negative lambda is precisely positive, which is exactly what we wanted. Okay, what we want for this thing to work. Okay. So sine of square root of negative lambda times L should be equal to 0. The L is outside the square root. Can anybody tell me what are the numbers? What are the positive numbers whose sign is equal to 0? There are not too many. There are not too many. But what are they? What are the positive numbers whose sign is equal to 0? Is equal to 0. So pi, okay, I agree, pi. What else? N pi, great. N pi where n is an integer. So we need to have square root of negative lambda times L should be equal to n pi. And if you solve for lambda, you will find that lambda is equal to minus n squared pi squared over L. Okay, that's how much lambda should be. So these are our eigenvalues. So these are the special values for which we have a non-zero solution. And now we can ask, okay, fine, we have a non-zero solution for this. What is that non-zero solution? And that non-zero solution can be taken. So again, lambda is equal to minus n squared pi squared over L. And the non-zero solution is going to be x sub n of x is equal, I'm taking C2 to be 1. You can take it to be anything you like pretty much. It's a constant. So it's sine of, so now I have square root of n squared over oops, make sure I wrote this. Yeah. So if I plug in lambda, I have to take the square root of negative lambda, and that is going to give me sine of n pi x over L. Okay. Let's see how this works, because the solution supposedly was sine of square root of negative lambda times x. So I'm sorry, there's a square here. Sorry about this. So when I plug in, this will be minus n squared pi squared over L squared times x. The negative signs cancel each other, and then you take the square root, and that gives you n pi over L times x. And that's it. So that's our eigenfunction. Okay. And at this point, I would like to mention, so if you look at the homework for next time, let me turn to the homework and see. So the first two questions are two eigenvalue problems, different from the ones that we saw here, but pretty much they're going to be solved in exactly the same way. So what are you going to do? You're going to take the first one, for example, y squared plus lambda y is equal to 0. you want x to be between 0 and pi, and you want y of 0 to be 0 and y prime of pi to be 0. You're going to solve it exactly the same way. So you're going to start with the auxiliary equation. And you're going to consider the cases lambda greater than 0, lambda equal to 0, lambda less than 0, and you're going to see when these conditions are going to be satisfied. Please notice that here you have the derivative being equal to 0. So that might change things in the final answer. Okay, I want you to understand that. Okay? Any questions, please? Why don't we take a 7-minute break, and then when we come back, we're going to see how we're going to use this in order to solve our to find the solution of our initial differential equation, and to realize how far we can go without introducing Fourier series, which will be our next goal, our next and pretty much final goal for this course. Okay, so let's take a break. Okay, so let's continue. And let me see if there are any questions here. I promise you that we're going to go through this whole process, this long process, at least once. But this is something that I will want you to do on the final exam. Okay, like this. So go through the process of separation of variables for the heat equation. So pretty much what we're doing today. So not much different than what we're doing today, but that's what it's going to be. So any questions so far, please? So let's complete this, and let's write down everything that we have so far from the beginning, so that you can all see where we are. So our original equation was the partial derivative with respect to t was equal to beta times the partial derivative twice with respect to x. And we said that beta is supposed to be greater than 0. And then we have u of 0 comma t is equal to u of 0 comma l is equal to 0, and u of x comma 0 is equal to f of x for t greater than or equal to 0. And the previous condition was for t between 0 greater than or equal to 0. No, I'm sorry. The last condition is for x between 0 and l. Okay, and we said that we were looking for non-zero solutions that had this very special form. Again, I would like to emphasize a lot that this is a really preliminary step in what we're doing. And this translated to the eigenvalue problem, x double prime. It broke, if you like, to two problems. X double prime minus lambda x is equal to 0. X of 0 is equal to x of L is equal to 0. And don't forget that we also had an additional equation, which was t prime minus lambda t is equal to 0. Now, from this eigenvalue problem, we found that the numbers lambda for which we have non-zero solutions are minus n square pi square over L square, and that the corresponding solution is xn of x is equal to sine of n pi over L times x. Okay, so this pretty much summarizes everything that we did before. Okay, questions, please. Questions. So now finally we need to turn to this equation and ask ourselves, what are the solutions for the specific eigenvalues that we found? So this equation actually is very simple to solve. It's t prime plus n squared pi squared over L squared t is equal to 0. This is a separable equation. To make a long story short, the solution is going to be e to the negative n squared pi squared over L squared times t. Okay, this is a separable equation. It's also linear. Any way you want to see it, that's a very simple equation to solve. And it's like this, which eventually gives us these specific solutions, sine of n pi over L times x, e to the negative n squared pi squared over L squared times t. And if you ask, this function satisfies what from the initial problem, then the answer is it satisfies these two. It satisfies these two. Nobody can guarantee here that it's going to satisfy the last equation. That's by no means true. Okay. So so then here comes the question. How are we going to ensure that the last equation is satisfied? And the answer is that, you know what, if you pay attention to the first two conditions, you will understand that they're linear and homogeneous. So the ones that I have circled in green are linear and homogeneous. And that means that if a function satisfies them, or if a certain function satisfies them, then any linear combination thereof will satisfy them. Which means right away that you can take a function that looks as general as this. So look at what I'm going to do. I'm going to take all these functions that I had, and I'm going to multiply them by some numbers and then add them all together from 0 to infinity. And basically I'm saying that this expression should be general enough to satisfy the initial differential equation if we can choose Cn appropriately. So we hope, okay, you're going to see that it's possible. So we hope that for an appropriate choice of Cn's, okay, appropriate, I love this word. Please give me the attendance for the word appropriate. For an appropriate choice of Cn's, the third condition, or the second condition for that matter, it's the first being the equation, the second condition will be satisfied. So what is the second condition? The second condition is that u of x comma 0 should be equal to f of x. If you plug in u of 0, then the expressions e to the negative n squared pi squared over L squared times t become 1. So basically this translates to sum from n equals 0 to infinity of Cn sine of n pi over L times x should be equal to f of x. And now all of a sudden, a new need emerges. What need is that? The need of having the function expressed in terms of sines. That's the motivation for doing Fourier series, which is what we're going to do next time. However, with what we have in our hand so far, we can solve a specific problem. Somebody asked me for numbers, for a problem with specific numbers. So this is how specific things are going to get. So let's solve the following problem. The equation is the same, so ut, but now I'm going to tell you that I want beta to be 3, uxx, and I want u of 0, t to be equal to u of pi, t, and be equal to 0. So from here you can understand that beta is 3 and L is pi, and then I would like u of x, 0 to be. Now I'm going to be very specific, so I'm going to say 5 sine of pi of 5 sine of x minus 4 sine of 2x. And I claim that this particular problem we can actually fully solve. I claim that we can fully solve this particular problem. Okay, how? This problem looks very much like your third problem. Okay, here's what I want you to do. I want you to go through the whole process that we explained today. Give all the details. Provide all the details. And when you do so, you will be working with instead of beta, you will be writing 3. Instead of L, you will be writing pi. And eventually you will find, so after you work all this problem, you will find that u of x, t has to be equal to sum from n equals 0 to infinity of Cn sine of, now let's see how this is going to turn out. Remember, what was this? Take a look at this. It goes n pi L over x, but now L is pi. So pi and pi cancel each other. And what you get here is nx. And e to the negative what now? You had n squared, pi squared over L squared. Since L is pi, you will get pi squared over pi squared. So this will be n squared t. So this is what function we will be able to find, right? And now pretty much what we're saying, so this function given like this is guaranteed to satisfy what? These two conditions, the equation and the first condition. But we're not just staying with that. We wanted to satisfy pretty much the last condition too. So we want u of x, 0 to be 5 sine x minus 4 sine 2x. Which means what? That the sum from n equals 0 to infinity of Cn sine of nx has to be equal to 5 sine x minus 4 sine of 2x. I want us to break this down concretely. I want us to concretely see what this means. What does it mean? It means that first of all, you know what? I think I've been making this silly thing all along. It shouldn't be n equals 0. For n equals 0, this is, so it's from 1, not from 0 to infinity. Because sine of 0x is 0, and it doesn't, let me see if I have done it anywhere else. Yeah, I have done it here. So n equals 1. Okay, n equals 1 in all of these equations. My apologies for this. And so I will have C1 sine of x plus C2 sine of 2x plus C3 sine of 3x plus, and so on, being equal to 5 sine of x minus 4 sine of 2x. Okay. So this tells you that this C1 has to be 5, right? Because they're both sitting in front of sine x. The philosophy that we're using here is that when you have two series of sines, for them to be equal, the coefficients have to be the same. And the C2 has to be exactly this -4. And everything else should be 0. Okay, so basically what we're going to have is C1 is equal to, what was it, 2? No, 5. And C2 is equal to -4. Is -4, and C3, C4, and so on. All of them are equal to 0, all the other ones. And now I can write down the function. So u of x comma t is going to be 5 sine x e to, now I can tell you what n is. N is 1, right? E to the negative t minus 4 sine of 2x. And now what is n? N is equal to 2, so n squared is equal to 4. E to the -4 t. And that's your solution. And that's as good as it gets, right? I mean, think about it. We just found a very specifically written solution of our partial differential equation that satisfies the equation and the two conditions that depend on the boundary of that set. And that's all. Okay, so that's exactly what I'm asking you to do in the last problem of the problem set. And when I put here this dot, 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 the dot, dot, dot is the 2 pages of work that I showed you before. So I want you to go through the separation. I want you to go through pretty much giving everything that there is to give in that context. Okay. Any questions? So this does require a lot of work. Okay, there's no better way to put it, because that's the only way to put it. So yeah. Okay. Okay then. So like I said, we are going to go through the whole process at least once more, and you will see that that will become even more times when we do our review. Okay, because like I said, the work that we did today, like this, so I will give you an eigenvalue problem to solve, and I will also give you a problem of a heat equation. I want you to really know all these steps, okay? And that will be all for today. I hope you all have a nice rest of your day. I'll see you on Wednesday.